Let's analyze titration curves. The first curve that we're going to analyze has this appearance. You can see that we're starting at low pH, pH lower than 7. That's how I know I'm starting with an acid. So in my Erlenmeyer, I have an acid. In my burette, I have the strong base is given as sodium hydroxide. So I know that we're starting with an acid. We're titrating an acid. And this is a strong acid. Very important, strong acid with a strong base. How do I know that I'm titrating a strong acid with a strong base? Well, we know it's an acid, but you can see where the curve changes from concave up. This portion is concave up. This portion is concave down, where the curve changes concavity, called the inflection point. This point right here, this is the equivalence point, and you can see that the equivalence point is at pH 7. When the pH is at pH 7, we know that we are titrating a strong acid with a strong base. Let me write down some equations so that we can understand why it is that the pH is 7. When we react hydrochloric acid with sodium hydroxide, and I just picked arbitrarily, it could have picked any strong acid, but I picked HCl, any strong monoprotic acid. We don't make a salt, but we've got an aqueous salt, meaning sodium ions and chloride ions roaming about in solution, and we have water formed. So the question, we know that water is neutral, pH 7. What about the ions? Do the ions hydrolyze water, meaning do the ions react with water? And in fact, sodium ion does not react with water, neither does chloride ion. So the sodium ion and chloride ion are pH neutral. You can see that the second curve that we are examining, we're starting with a pH higher than 7, so we know that in our Erlenmeyer flask we have a base. And in the burette, we have a strong acid, and in this case it's HCl. So we are titrating a base with a strong acid. What kind of base? This is a weak base. When you titrate a weak base with a strong acid, the equivalence point will be at pH lower than 7, and in this case the pH is 5. Let's examine, by looking at some reactions, why it is that the pH must be lower than 7. Remember from the previous slide that the chloride ion is pH neutral, but what about the ammonium ion? Does the ammonium ion hydrolyze water, meaning does it react with water? Ammonium ion does in fact react with water. The extra hydrogen reacts with water, and ammonia is formed, and hydroxide ion is formed. In the hydroxide ion, not the hydroxide ion, the hydrogen ion reacts with water to form ammonia and the hydronium ion. And the hydronium ion is the strongest acid we know. Because the hydronium ion is formed, the strong acid, the pH at the equivalence point is in the acidic range. What is the equivalence point? When equal number of moles of acid have reacted with an equal number of moles of base. So we have an equal, at this equivalence point, where the concavity changes from concave down to concave up, the equivalence point, this inflection point, we have an equal number of moles of ammonia reacting with hydrogen ion. In the last curve that we're going to look at in this video, I want you for a moment to ignore all these labels. Ignore all these labels. Just look at the curve. You can see that the equivalence point here is at pH 9, which is in the basic range. The equivalence point, is at pH 9. The basic range. That tells me that we are, and we know that we're starting out with a weak acid. That tells me that we are titrating a weak acid base. So in our Erlenmeyer, we have a weak acid, and our burette is filled with a strong base, in this case, sodium hydroxide. Let's examine the reactions to understand the reason that the equivalence point is at pH 9 in the basic range. I'm picking acetic acid, a weak acid, to react with a strong base, sodium hydroxide, and what forms is the acetate ion plus water. So this hydrogen from the acetate ion, from the acetic acid, the hydrogen ion reacts with the hydroxide, because remember what this is. This is sodium ion and hydroxide ion, because sodium hydroxide is a strong base, so it's aqueous, and just the spectator ion is still present. So the question is, we know from the first slide, sodium ion is pH neutral. We know water is pH neutral. So the question is, does the acetate ion hydrolyze water? Does it react with water? Oh, one thing I should mention, notice I'm always drawing the double arrow whenever we're working with a weak acid or base. So in the previous slide, we were working with, we started with a weak base and reacted it, so we had a double arrow. Only in the first slide, where we were working with a strong acid and strong base, did we have a one-way arrow. Okay, so does the acetate ion react with water? It does react with water. The acetate ion, this acetate ion abstracts the hydrogen from water to form acetic acid and the hydroxide ion. Remember that the hydroxide ion is the strongest base we know, and that's the reason that at the equivalence point, the solution is in the basic range because of the hydroxide ion. Now let's focus on, because of the hydroxide ion, very strongest base we know, that's the reason the equivalence point is in the basic range. Now let's try to understand what all these labels are. Okay, so we're starting with a weak acid, pH is lower than 7. Here's the equivalence point. And here you can see that this is labeled as the buffer region. And the reason for that is, let me reiterate what the equivalence point is we have as many moles of acid equal moles of acid reacting with equal moles of base. That's the equivalence point. But before we get to the equivalence point, we have a lot of acid and we're adding hydroxide ion. So as we add hydroxide ion, some of the acid is reacting with the hydroxide to form acetate. So you have some hydroxide ion and some acetate ion here. So this is the buffering region. Notice that it takes about, let's say, 28 milliliters of sodium hydroxide to get to the equivalence point. If I take the 28 mils and I divide by 2, that's 14 mils. If I go to 14 milliliters, right here, this is 14 milliliters, that would be the half equivalence point. And you can see the half equivalence point is at pH 5. So the half equivalence point means you have the concentration of acetic acid. So half the acetic acid molecules have reacted, forming acetate ion. So the concentration of acetic acid equals the concentration of acetate ion at the half equivalence point. We will learn later that the pH at the half equivalence point equals the pKa. So at the half equivalence point, the pH equals the pKa. So this means that pKa also equals 5. This would allow us to find the pKa of the acid. Since pH equals negative the log of the hydrogen ion concentration, pKa equals negative the log of the Ka. So if pKa is 5, that means that negative 5 equals log Ka, and we do take the inverse log of both sides. 10 to the minus 5 equals 10 to the log Ka. So that means that 1 times 10 to the minus 5 equals the Ka. So this is the Ka of this acid. That's it for this video. We'll do more on pKa, and thanks for watching.